You guys have a good weekend? Celtics lost. Stupid freaking Cavaliers. LeBron James. Need to break him up and make a few people out of him. Anyway, they're in the playoffs. So that's awesome. I don't care. I just live in the first quarter. All right. So before I get into it, any specific questions on anything? Chapter 7 even. Remember we did that p-hat stuff, the confidence intervals?
I have a question on 7.2. For 34 and
All right.
the ones where they don't tell you anything.
Oh yeah. It seems like they don't tell you anywhere near enough, but very slight OCD. Very slight. Not monk level. Yeah, so number 34, Windows penetration. That sounds very strange. How many computers must be surveyed in order to be 99% confident? This is awesome. That's actually all I have to tell you. It's freaky. So this is number 34 in 7.2. How many to be within, what's it say? 1 percentage point. At 99% confidence. So the hardest thing I think about this when you talk about proportions is you've got a percentage that they have to tell you just so you can figure out your z-score. Right? Can somebody tell me why this statement leads to a z-score? I love that question. I might put that on a test. I don't know. Why does that lead to a z-score? If I tell you 99% confidence, 90% confidence, why does that lead to a z-score? Sure, that's what you do to figure out the z-score, but why does it lead there? It's a percentage, sure. And what's the relationship between the percentage and the z-score?
This is the outside of the probability.
So if I want to be 80% confident, I have to go out this far, because I have to go out that far. That z-score tells me how far I've got to go out to catch 80%. If I want to be 99% confident, do I have to go further out? Hell yeah, I got to catch more. Right? Catch them all. So, okay. The statement about confidence really just has to do with the z-score. People freak out because there's a whole other percentage up there, but we're talking about a confidence level for a proportion, for a percentage. And of course, what is this going to be related to? The error, because that's what I want to be within. I want my percentage, so I want to be able to say it's 40%, give or take, a percentage point, whatever it is, 39 to 41%. I want to be at most off by 1% in either direction. Does that make sense? You guys with me? That word within, that's what that means. Guess my age, and you could be within 2 years. That's how much error I give you, how much room I give you to be wrong. So what's this tell me as far as the z-score goes?
2.576.
Yes, cool. 2.576. And let me see if this book, do they tell you blah, blah, blah? No, they just say to do it. In reality, I'd have to have some way of knowing that this was normally enough. But we're just going to plow forward, all right? So that level of confidence tells me I've got to go that many standard deviations out to catch enough data, to catch 99% of the data. So I'm 99% confident I caught something specific. And then, what's the formula for this?
Z squared.
Good, z squared.
P hat, Q hat.
Some hat things.
E squared.
And it's always e squared on the bottom, right? Okay. I'll let you absorb that for a second. course, they don't make you memorize formulas, they make you recognize formulas. But this is pretty easy. When I ask you how many, that tells you I want a formula that's solved for n, because I don't know how many. I hate teaching it like that, but now that we've talked about it, you can look at it like that. So now I just got to fill it in. Now, what's part A say specifically? Does part A say something? Or is it just blank? Are they messing with you? Like, what can we do to these students? It's already hard. Let's just give them a blank question. What's it say? Sham, did you ask this question? You don't remember? Laura's helping me.
Well, it's like that you don't know.
Yes. You don't know shit. So that was part of your question. You actually know a lot. You knew enough to get this, right? Because they told me you know enough to get this. And of course, if I don't know what either one of these are, I have to assume that they are, it's 50-50, which the product would be 25%. I love it. So now you got everything you need. You throw in there this 0.25 for your 50% times 50%, divided by, what's the bottom going to look like? Good, good, good. From the t-score chart, right? If we want to be 99% confident, how much is outside in two tails? 1%. So look at 0.01 in two tails. Go all the way down to get a z-score.
Which one is it? Oh, yes.
Because if you stop, you get a t-score.
Yeah.
How do I know, what is it about NPQ problems I told you guys about? What is it about NPQ problems? It's either normal and I can use a z-score, or do I ever have to, can you, or do you ever have to use a t-score with an NPQ problem? No. Because with NPQ problems, we always make our own population standard deviation. We make it. So do we ever not know it? No, because we make it. Every time we make it. So why were t-scores invented? Why were t-scores invented?
It's already known.
When you don't know what?
Standardization.
Standard deviation of the
Population.
population. Cool, right? We can always get the standard deviation from our sample because we've got the sample. We're holding the sample. I can get the standard deviation from it, right? So, let's try to put this all together. You ready? T-scores were invented for when we don't know the population standard deviation. Whenever I have an NPQ problem, I calculate my own population standard deviation. Therefore, I never need t-scores with NPQ problems. It's awesome. Let that be really, really nice. Right? You can always use z-scores as long as it's normal enough. And how do I know this is normal enough? The book said just do it. And we're like, all right, whatever. Yeah.
So basically, we're using that t-score chart to get a z-score value, right?
Beautiful. Because at the very bottom of that t-score chart are z-scores. And the way it's set up just makes it easier to use.
But even if you give us like, I don't know, like 85 or 90%, like confidence interval, we use the large sample, large degrees of freedom on the t-score.
So if you're allowed to use a z-score, you can use the t-score chart to find them, unless I'm asking you to make some weird-ass confidence level that's not on there.
And then we use that closest form, right?
No. If I said 94% confidence here, what would you do? Besides go somewhere and cry, what would you do? Use a z-score chart. Do it the old-fashioned way. Right. And now I just got to throw this in the calculator. So again, the question said how many. So I know I want to use a formula that's got n. Solve for n. So I can figure out how large the sample has to be. Confidence level always tells me my z-score or my t-score. Laura, we're going to ask them? All right. Is there anything else about that one there? Is that all right? All right. Part B on that just says, assume that a recent survey suggests. So A, we didn't know what P hat and Q hat were. B says, assume that a recent survey suggests P hat is 0.9. So then you just do it all again. Instead of 0.25, you're going to have 0.9 times 0.1. That's crazy. I like it. And then you can see how the sample size requirement changes.
I think for 35, I was just more like confused on how to get the T-score for that one.
So 35, is it talking about a mu or a proportion?
Sample.
Is it talking about a mean or a percentage?
Oh,
Yeah, totally, right? And it's actually in the section that's talking about estimating proportions. So it's kind of a gimme. And what did I say earlier about percentage problems, NPQ problems? What can we always use as long as it's normal enough? We can always use Z-scores. We never have to use a T-score. Yeah. All right. So anything else from homework? So on 35, just to finish this one out. $35 is the same exact problem as 34, really, except it's just talking about Twitter now. And it wants us to be 90% confident that we're within 5 percentage points. For 90% confidence, what's the Z-score going to be?
1.6.
Sweet. So you got 0.10 and 2 tails. You can look at your T-score chart. 0.10 and 2 tails. Go all the way down.
where did you get the 5 percentage points?
In the problem, it says, how many adults must you survey to be 90% confident that your estimate is within 5 percentage points of the true population percentage? So that was the problem. All right. You didn't know what your E was. So again, this is not always going to be the word they use, but this is definitely a very often used word. What's the word that tells me I'm dealing with an error right there? Within. I'm not saying it's always going to be within, but it's going to be something like within. And normally it is within, because that's the one that makes the most sense. You know, guess my height within 2 inches. You know, within is just natural for us to say. So that should be the word you see. All right. Anything else from homework? The homework is going really well then? All right, so what you got? Come on. Now's the time for us to go over something if it doesn't make sense. Or you could come to my office. That'd be really good. So let me tell you this. One thing I don't like about this book is... Say again?
What is that? Do we have a quiz this week?
No. Huh?
Next week?
I will tell you. I'll tell you when I know. The book writes the confidence interval something like this. And then they have like an extra thing. So I always write this as one compact little statement. So this dude is the dude we created last time. Okay. And we created it based off of what we already knew from before. We divided by n to try to get the p's by themselves. And there's always 2 main things going on. There's the idea behind something, and then there's a technical aspect of how to just use it. Right? So there's the idea behind a confidence interval that if you go out so far, you're going to catch so much stuff. So of course you're going to be that sure that that interval catches a specific thing. So if you got the real percentage out there somewhere, and you take a sample and you get a p hat, so if there's a real percentage of gross one students that believe in UFOs. You with me? There is. And we go out and take a sample. So there's a real percentage somewhere. We go take a sample. These are most likely not going to be the same. I'll put money on them not being the same because we're just taking a sample. If we construct a confidence interval around p hat, and I make it like 95% confidence, then roughly 5% of the time we will not catch this. So if I make a confidence interval, what's more likely? That it actually is in there or that it isn't? It's more likely that it is in there. But the mistake people make is they make that into it's always in there. The confidence interval is always right. And the same thing happens with researchers. They find what they think is significant results. They don't do enough after testing. They put it out there, this big splashy article, and then like a week later they go, oh, we might have been wrong. Well, freaking wait. There's a lot of pressure to come out and have some interesting, nifty results so you can get some funding. It sucks. It's stupid. You have to give them time to check their work. And not let some other dork go out there and say, we found it. And like, oh, we should have went first. And now they're the ones that are going to be screwed a week later. Oh, shit, maybe we're wrong. But this is the whole idea. Whenever we take a sample, we know it's not going to be the right value. It's not going to be the true value for the whole population. But what a confidence level tries to do is it tries to give me some idea about how close am I to the real value. The real value, my confidence interval is going to catch the real value such a percentage of the time. So it kind of gives me an idea how much I can trust that confidence interval. Yes, sir?
So what do you mean by P right there? P with no hat.
I love it. What the hell is P with no hat? The true percentage of the population. I love it. So P, just like mu is the population mean, and X bar, see how X is wearing a bar on its head? Because he's showing off that he's got really good balance, right? Sample mean. So for percentages, P is the population percentage. And P hat, yeah, they're cute. P hat is the sample percentage.
Thank you.
Anytime. All right, hopeful and hopeful.
So we're saying like, so P hat is UFOs or whatever students.
Yeah, so P hat would be if I went out. Let's create something real quick. We go out, we talk to. I don't know, say 104 gross one students. Truly random sample for gross one students. We talked to 104 truly random, morning, evening, all ages, whatever, right? All kind of classes. And we find 31 believe UFOs have visited their house. No, have visited California. All right. And to me, it's kind of funny because it's really easy to discount the idea of UFOs as being insane. But then as a scientist, you got to say, the universe is so freaking vast, who knows what the hell, right? So I am, some of you guys might think that I'm crazy for saying that, but you never know. Shit. We're here. The hell? Somebody else might be somewhere else. Found freaking permafrost. They found freaking water on Mars. Shit. Who knows? There could be something right underneath there going. We almost found us that time. Shit. Little rovers are like bouncing on the roofs and stuff.
Finding a percentage, like 31 over 104.
Beautiful. I mean, don't make this a big deal. There's a stupid little formula for this, but you don't need a formula. How do you find the percentage? The amount you're looking for divided by the total. Right? So if I'm looking for believers divided by how many atoms? So what's that going to be?
I don't have my calculator.
That's all right.
29.8%.
0.298?
29.8%.
Yeah, point.
And be real careful. You do want to write it as a pure decimal. Yeah. Just to keep weirdness from happening. So what's Q hat?
27.
Yeah. You ever tell you this? I've told you this, right? Make them 9 and make the last one 10. So 7, 0, 2, bang. Or use a calculator. And now we just use this formula. Right? We got, let's see. Well, now I got to tell you. What do I still have to tell you before we can use this? Yeah, so construct. I love that word construct. You like, I wasn't told I was going to need hammers and stuff. And what do I need, a level? Do I need a t square? No. Construct a confidence interval. Let's say a 98% confidence interval for the true percentage who believe of believers. Not believers, but believers. So they always have to tell us less than it feels like we need, because once they tell us this, we can calculate this, and that's what I need there. So they're kind of like doing double duty. So these problems are always a little shorter than we expect them to be. They don't have to tell me as much. So what's my point estimate? What's my best guess? That's what point estimate means. What's my point estimate for the percentage of people that believe in UFOs?
29.8.
Yeah, beautiful. Because why is that my best guess? Because that's what I freaking went and saw, right? So what I saw that. So that'll be 0.298. That's my point estimate. Give or take. What about for 98%? Who's got that going on? What's the z-score for that? What would alpha be? Let me remind you about alpha. What would alpha be? If 98%'s here, what's outside?
2.
So alpha is 2%. 0.02 and 2 tails. Yep.
0.326.
Beautiful. Times the square root of p hat times q hat divided by n, which I've already forgot, 100. All right, and you get the error first, so you know how close you are. What, give or take, how many percentage points? You calculate the error first. You guys are going to want calculators today, so if you want to borrow a calculator. Oh. So see what we get here. One 104. I got 104. Anybody else get that? I could be wrong, you never know. Pretty sure I'm not. Been known to be wrong. All right. So that's like, what is that? That's like 10 percentage points. Why is it so big? Why is that so big? Yeah, two things. I want to make a pretty big confidence interval, but I also only talk to 104 people. And normally for these, you want to, like Gallup always talks about 1,200 people or something, and theirs is always plus or minus 3 or 4 percentage points. We talk to 1/10 of that, so we're going to be 1/10 as sure in a way. You guys with me there? Our sample size is relatively small. 104 is a decent sample size, but it's relatively small. And that's why we're off by 10 percentage points. Shit. So then it could be anywhere from 0.194 to what you got, Jeff? 402 then. So we are 98% confident that this interval contains the true percentage of gross response students who believe that UFOs have visited California. I don't know if they themselves saw the owls at their window. Who gets that reference? Nobody. Okay. So these are kind of nice. It's kind of nice that they don't have to give us as much information. Don't freak out. Don't go, they didn't give me enough. You don't need to be told all that much.
So we just say we're 98% confident that the true percentage is within there.
So we are 98% confident that our interval 19.4% to 40.2% contains the true percent of gross 1 students who believe in UFOs. Too many words. Okay. So in the book, the instructions have like part A, B, C, D. A through C is this. So don't freak out. This is A through C in the book if you're doing the homework. Part D is write the statement. So they break it out to part A is figure out the point estimate and then figure out the error and then do the well, okay, we do all that. We do all that. That's part A for me. And then you write the statement. And it is, I'm sure some of you guys have realized that I took some point off. You got to say, because the true percentage doesn't move. It's sitting somewhere. It's our intervals that could, I think this interval caught it. I won't say that the percentage is in my interval because it's not the percentage that's moving. It's my interval that's moving. So I want to say that this interval contains the true percentage. It's a very slight semantic thing, but it's important. But the basic idea of confidence intervals is almost too simple to believe. Just go out far enough to catch 99%, and guess what? You're 99% sure that you caught the mean. It's crazy, or the percentage in this case. It's kind of crazy. All right. So there's no other specific questions or anything? We're going to get back into chapter 8. And I got my little handout to help us out today. Well, I'm going to start. So what we're going to do, just so you know kind of like where we are, Section 8.2 is the section that breaks down each step of the 5 steps. It breaks them all down. So the one homework section deals with one piece. Another one deals with another piece. 8.3 is where you have an entire test that you have to do. And 8.3 is the testing for proportions that we haven't actually talked about yet. 8.4 is the testing for means. I like that. You can meditate. You can do whatever you need to get through. All right. Just don't be too loud on your ohms or whatever your mantra is. Celtics. All right. So I'm going to do one example, and I'm going to fill in all the little technical details, and then I'm going to give you the handout that really actually explains every step, but it's actually a problem. So then you're going to have to do it yourself. But every step is fully explained. So I'm hopeful. Yes? Yes, good. This is the one we did last week about the... Huh? No, 5 steps. When I learned it, it was 8 steps. I said, get away. I made it 5 steps. So again, you're welcome. All right. So let's make something up real quick here. Let's see. We feel that the mean this is actually section 8.4.
Okay.
Yeah, you got to trust me on this. The only way that it makes sense to me is to do entire problems at a time. Section 8.2 will then test you in every section individually. It won't do an entire problem. We feel that the mean wait time at the DMV is more than the claimed 15 minutes. Sure. All right. That's our claim there. We feel that it's more than that. let me not use this word, more than the stated. There's the word claim has a special meaning. We take a sample of 38 DMV waitees and find a mean wait time of 21.9 minutes with the standard deviation, 8.02 minutes. Let's see how this works out. Should be interesting. Because you always got those people that come in and all they need is one little form and they say, go ahead, go. And then they give you the 8 forms. Sit down in the back if you can find a chair. If you can find a chair, you might not want to sit in it. I don't know. All right. So test the claim using alpha equal to 0.01. Sure. Okay. Where are we at? Sorry. So we feel that the mean wait time of the DMV is more than the stated 15 minutes. We take a sample of 38 DMV waitees and find a mean wait time of 21.9 minutes. So standard deviation of 8.02 minutes. So we want to see, is this enough evidence to back up our claim that it's more than this? Now, of course, 21.9 is more than 15. Ooh. If it wasn't, I wouldn't even do the test. I go, well, shit. So if I got a sample and I got an average of 13 minutes, I'd go, oh. I wouldn't do anything. Why would I even get into the test? Already I know it's crap. So at least it is more. The whole purpose of the test is it more enough? Because this is just a sample, and I could have just happened to pick a lot of people that had to wait long, right? Because the people that didn't have to wait long were gone before I could turn around and talk to them. Who knows?
So, is that an X or is that like a little fish?
Where are we at? That's a little fish dude, right? Alpha. Cool, I like it. Little fish dude. So, step 1. All right, let's be really specific here. Step 1 is always, what the hell are you talking about? Step 1 is where you start. The very first thing you look for is your claim. And you write it in Mathish. So what's my claim? Good. Our claim is the mean is more than 15. I never have my sample data show up in my claim because I make my claim before I take the sample. Right? It's just that they got to give me the whole damn problem for me to do it. But in real world, I make a claim first and then go take a sample. So the mean is more than 15. All right. So here we go. Here's the first introduction of something interesting. So last time I talked about the fact that there are 2 stances then. There's the claim and there's the opposite. So the 2 things are hypotheses. So you have what's called the Null Hypothesis. And right now there's somebody going, oh God, that sounds great. And so this is given the symbol H naught. That's a circle. That's an O. Sure. Either way you want to look at it, they're the same thing. So it's an H with a... I call it the ho. Just to make this a little less crazy. Or a little more crazy, whichever way. And then there's the alternate hypothesis, which this book calls H1 for some reason. The book I used to use called it HA, which made it better because then you had the ho's and the highs. But now you get the ho's and the highs. That works. The high hopes, yeah. Be careful about that. All right. My dean's going to be like, you were calling everybody a hoe? So here's the thing. Just the way that we set these tests up. H1 will always be the one that tells me how many tails I've got. So if I want to... how many tail tests will this be and where will the tail be? Can you tell me already? Before we get, what do I want my sample to do? Where do I want it to end up? In the middle is going to be 15, because we're going to assume that's the real mean. I want to show evidence of my claim. Where's it got to show up? It's got to show one place. And so it's a one-tailed test. It's got to show up here, right? So I already know that this is going to be a one-tailed test. In order to work, I got to find my sample way out there. It's a one-tailed test. It's up there. So HI is going to reflect that. So my claim happens to be that HI is going to be that. HO will then always have an equal sign because of that. Let me say that again. And the book uses an actual equal sign. I don't, but you could do either way. I do the real opposite of that because that's the way I was taught, and I don't see any reason not to do it that way. The book just always puts an equal sign. So what's the opposite of mu greater than 15? Less than or equal to 15. So if my claim had an equal sign in it, I would have put it here because the HO always has the equal sign. That's just the way we kind of structure this thing. And then my tail, my area where it's going to show evidence, is always set up by H1. So it's that. Let it be simple. If my claim was, I think it is 15 minutes, it would have been mu equal 15. That would have been HO. Mu equal 15. Why? Because it has an equal sign. You got a semi with me. So don't think that the claim is always H1. That's not true. In fact, today we'll see a case where that's not true. All right, maybe. Yes, ma'am.
So you use null when you're trying to figure out that something is a certain value?
I like it. You can never, ever prove that something equals something using a sample. Let me say this again. Does this make sense? I cannot prove that the average age of gross wine is 27.3 by taking a sample. Do you guys understand? But I can certainly show evidence that it's less than that or more than that if my sample is really far away. So the whole idea of hypothesis test is I can only show evidence by getting really far away from the middle. If I'm somewhere close to the middle, then I go, oh, I didn't find evidence of anything weird, so I can't say shit. Don't worry, you got to kind of go through this a few times so you really get it all down. Right now, HL always has an equal sign, H1 doesn't. Why did I put this there? Because it does not have an equal sign. And then you can always just look at this at H1 to draw this little picture to show you where you want to end up. All right, maybe. Again, you got to do a few of these to get it to sink in. Right? Just think about all the shit you know now that you had no idea on day one. So this is going to be one of those things soon, hopefully. All right, so step one, what the hell are we talking about? These are the two ideas. Either it is greater or it's not. So I can show evidence that this is true, or I can fail to show evidence that this is true. So I fail to show that this is false. Does that make sense? So I can either, it's a little early for this, but I can reject this guy. If I reject this guy, what does it mean about this guy? If I say you're wrong, then I must be saying he's right. So if I reject him, I support him. Or I can fail to reject him. I can fail to say he's wrong. I can have a sample that's too close to the middle. It's not proof that he's right. It's not enough evidence to say he's wrong. And we got to do a few of these before it really kind of kicks in. And I know you're all like, oh my God, math people, don't be doing all this grammar shit. No, this is not your strong point. But this is important. This is actually very, well, we got to do a few of these to get the feel of it. So if I fail to reject him, if I fail to say he's wrong, then I fail to say he's right. Because they're opposite ideas. Don't make more of that right now than it is. You know, like, dude, it's not going to take much for me to make more of this shit. All right, just hang on. Second step. These will go a little bit quicker when you don't have me explaining the hell out of everything. So don't freak out. We're on the second step of 5. First step, what the hell are we talking about? Second step, what can we use to talk about it? Am I allowed to use z-scores or do I have to use t-scores? Why?
It's greater than 30.
All right, n equals 38, which is greater than 30. That means what? It's normal enough. Cool. I like it. So it's normal enough. But what? So that means I can use something. All that means is I can use something. What determines Z or T? Yeah, which standard deviation do we know? How do you know it's a sample one? Because it's Simpsons. Yeah. We take a sample and we find these two things, right? Oh shit, so that's S. So don't say we can use Z-scores because you tell me the standard deviation. I have to tell you some standard deviation. It's which standard deviation do you know? I don't know the real one, I just know the one from my sample, so I've got to use T-scores to cover my ass for not knowing the real one. So it's a two-step process. It's got to be normal enough or you can't do shit. If it's not normal enough and you got the balls, you can say, I can't do this problem, Jeff, and you go to the next one. I would highly recommend you still do it because you might have made a mistake somewhere. Yeah?
Where did you get the 30 from? Sorry.
Yeah, where is this from?
I don't think you got my data last time.
Chapter 6. 6 and 6.4, 6.5. It's the central limit theorem, right?
Anything greater than 30.
Chicken, lettuce, tomato. CLT. So that said, as long as it's greater than 30, then my sampling distribution where I plot the means, it's normal enough. So that's the magic number for that.
No matter what you're talking about, 30 is good.
And now if I'm talking about NPQ problems, what's got to happen? For NPQ, what has to be greater than? NP's got to be bigger than 5, and Q's got to be bigger than 5. You with me? So throughout all the statistics, and again, stats 1 is just a taste of everything, and you're like, well then I don't like that meal. But I understand. Some of you guys hopefully maybe do. Every single little distribution has its own way of telling if it's normal enough. So if I have this kind of continuous thing, all I got to make sure about is that the sample size is more than 30. Then I can say it's normal enough. Very often this is too strict, but we just use 30 just so we're certain. You guys kind of with me? For a binomial, NP and NQ, got to check those. Make sure they're both at least 5. Then I know it's normal enough. Other distributions have their own little things that have to happen. Okay, cool. I like it. So then, therefore, S is known, sigma not known. So which one do I use? T-squared. Kick ass. Because that's where they were invented. They were invented to help me when I didn't know the real standard deviation. So what are we talking about? What are we allowed to use to talk about it? And then the third step and the fourth step are really the heart of the problem. The third and fourth step are what's enough, how far do you have to be to show evidence? It's sort of like the coach trying to get somebody who's really fast. And he says, all right, you have to run at least this fast on the whatever yard dash. Obviously, I do that a lot, right? So that's evidence. If you can do it before that, then that's evidence that you should be on my team, right? So 3 would be setting that benchmark. 3 is what's called the rejection region. I haven't called it that before, but that's sort of like setting the benchmark, and anything beyond that is what we call the rejection region, which kind of makes sense. If I set this up, and I know it's a one tail up there, because it was all about being greater than 15, right? I'm going to show it takes me more time to get out of the DMV than 15 minutes. If I get my sample in here, if my sample's way out there, what's it seem is true about this guy? Does this guy look like he's right? If I get a sample way the hell up here, and here's 15, in the middle, we're going to assume that's the middle. We're like, sure, that's the middle, sure. If my sample is there, what can I say about this? I can reject it. So, and then the rejection region. So it makes sense. The name, oh my God. It's the region that if I get into it, I'm going to reject. Yes, I'm going to reject the hope. Yes. Knew that was coming. Sorry. If I offend you, wait a few more minutes and I'll do it again. That's what happens to my standard. Because I actually offended somebody once and I said, well, I'm going to do it twice before the day's up. So now all I want to do now, the real step here is, what's the z-score to tell me what's far enough away? So one way to look at this, which is not always correct, but it's good, it's perfect for right now, just to get a feel for this. These people here say it's 15. It's not more than 15, it's 15, around 15. And we're like, no, it's more than 15, you crazy ass people, right? So so somehow I got to set up my sample. If my sample is far enough away from 15, far enough above 15, then that's evidence that 15 is wrong. Does that make sense? It's sort of like what we've been doing several times over this whole semester. Yeah. Beautiful, I love it. Okay, so that's where I'm leading to. Because is it impossible? If 15 really is the middle, if it really is the middle, then it's not impossible to get a sample there, is it? You guys with me? If 15 really is the middle, it's not impossible. But the fact that we did it, and the fact that the probability of doing it is very small, how small? Well, eventually it's going to be this small, right? There's a 1% chance that it just happened randomly. So what's more likely? That it just happened randomly, 1%, or that this really is not in the right place, that it's more? What's more likely? It's not in the right place. There's only a 1% chance that was going to happen. And what do I do if that does work? I don't publish something about this. If I'm checking out medicine or something, I ask somebody else to replicate it. Or somebody else I know is working on it and say, how close are you guys? What are you seeing? And if they got way the hell up here too, I'm like, well, shit, let's publish. Verification. You get somebody else to double check your work. Because maybe it was just you happened to pick randomly. But what's the probability that two groups of people happen to randomly pick things that are up here when really it shouldn't be? Very small. 1% of 1%. Now we're talking about, holy shit, that is not going to happen, basically. There's still, what I love about statistics is there's still a chance we're wrong. There can never be a 0% chance of being wrong. Never. You can never have 100% safety anywhere. You're trying to get that way, right? But you can't ever get there. So stats is very honest. It says you can double check, you can triple check. It's never going to be 100% accurate, but you can get it really damn good feeling that it's true, right? Okay, good. Maybe. So if alpha is 0.01, alpha is, again, what's alpha? Besides the little fish dude. What does alpha tell you? The area and the tail, or tails. And how many tail tests was this? One tail test. So if you look at the t-score chart, we need a t-score, right? Even if we needed a z-score, we can still use it. What else do I need? So I got one tail, 0.01, and how do you know where to stop? What do you need to figure out? Yes, good. N-1. Degrees of freedom, N-1, which is 38 minus 1, 37. So look at your t-chart. Look at the column that's got 0.01 and one tail. Because it's a one-tail test. And I told you before, confidence levels are always two tails. And I said, we're going to get to these test things that could be one or two tail. Here we go, one tail. 0.01 stop at 37. And I get somebody tell me it's why I put a Z to T here. 2.431. Yes, ma'am.
Because I remember on the homework it was like you just go straight to the bottom and Z-score.
Z-score, I know, but here we're using a T-score. I like it. So if you stop, it's a T-score. If you go all the way to the bottom, it's a Z-score.
So I don't want to way past it, but how do you know it's the one-tail problem?
Right here. In order to be two tails, my claim would have to be, we think it's changed, or we think it's different. How are you different from something else? More or less, two tails. You don't care which way your sample goes, it just has to be far away in some direction, right?
So we just say it's greater, so...
Exactly. So if you can't find a word like greater, we feel it's increased, we think it's gone down, we think it's less, we think it's more. If you can't find a word like that, it probably is a two-tail test. Because they could be a little bit subversive. They can kind of hide. All right. Oh, we're 60% of the way done with this problem. All right, let's see. What do we need here? Here. All right. Let me erase that here. And then I can finally shut up for today for a little while if we get done with this one. So number 4, step 4. So now that I've set up what far enough away is. Ooh, and before I get too far from this. If you guys remember I said something about that T star, Z star, that's the score I get from my sample. So if my sample score is how related to 2.431, we'll find evidence. So if T star is greater than 2.431, what would that mean? Careful. If I'm this far away from what this guy thinks, what must be true about this guy? We can reject him. So if T star is greater than 2.431, reject the hope, support the high. Right? Of course, that's a very interesting phrase for today, if anyone's understanding. If you guys like whatever, dude. I don't understand half of what you say. I understand. Let's do it. I think I understand less than that, Jeff. Let's do a test. Yeah, T star is going to be my calculated score for my sample. So this is a T score. This is what the book calls T critical or something like that. It's just the benchmark. That shows me what far enough away is. What am I going to do now? Go take a sample and see, did I get far enough or not? So step 3 and 4 are the real heart of the problem. Right? Somebody had a gun to your head and they said, figure this out. You would only do step 3 and 4. You would screw the rest of it, just because these are the ones that tell you the answer. So 4 is sample data leading into a T-score. Now, real quick, what's the formula for a Z-score? We talk about means, so X minus, you can do it. Over the new standard deviation, right? That's the Z-score. It's basically always my data minus the middle divided by the standard deviation that I need to use. Right? That's the same exact formula for a T-score, so don't freak out. They're the same. So sometimes I'll use Z when I mean T, and I don't care. It just means the score from your sample. Who cares what you call it? So we'll call these T star. So what do I know for my sample? X bar was 21.9. S was 8.02. What's the new standard deviation going to be? Square root. So somebody help me out there. And I see some of you guys putting the whole thing in the formula. That sure, what the hell? That's fine. It's beautiful. I just got to do this first. 1.30. It's like 300. 301. 301. Okay. So then you calculate your score like we've been doing for quite a while, right? It's going to be our data minus the middle, which is accepted to be 15, divided by the correct standard deviation. I'm going to get something semi-crazy here. 4 point something or other, I think. At least. 5 points.
5.3.
What is it?
5.304.
Okay, I'm not surprised because I just made this up out of nowhere. But that's T star. So again, step 3 says how far must you be, and step 4 is go see how far you got. Kind of makes sense. How far you got to get, coach? This far. All right, let me go see if we can do it. Did we? How far do we have to get? 2.431. How far did we get?
5.04.
5 point. Holy shit.
Quarter down.
Did we pass the test? Hell yeah. Do we find evidence that the middle's in the wrong place? If the middle's in the right place, look what we just did. Holy shit. Let me say this again. Assuming that's right. That's what we always do when we do high school. Assuming that is the middle. Look what I just did.
So what is the 2.431? What is that?
That was what?
I mean,
That's what tells me what far enough away is. So that is more than that. And where 2.431 come from? This dude. It tells me what far enough away is. So if somehow t was 6, we didn't get far enough away. T would never be 6. That's insane. That's like telling me that you got to bench press 800 pounds before I'll let you do something.
Far enough away for evidence that it is greater than 15.
I love it. So our sample was just so damn far up there that the real middle must be further up. Now, it doesn't say that the real middle is this. Where'd it go? I can't say the real middle is this, because this is just one sample. But that is evidence that the real middle is further up. Especially if somebody else did this test and found the same thing. The real middle was further up. All right. You're just in time to watch them work. Hey.
So then, what would the chance be that 21.9 is completely off? Like, it's not an accurate sample.
That would be, how do you mean it's not an accurate sample?
Like, it's
What's
a sample, but it doesn't accurately represent the mean.
That would be more dependent on how we collected our sample. Right? So unless they say otherwise, then you have to assume that it's a good random sample that they followed through. It's not a voluntary response sample or something crazy. Cool. So we're going to assume this is truly randomly selected. And if I do truly if this 15 was the real middle and I got a random sample, where should its mean show up? If the real mean of the population is 15, and I go take a truly random sample, where should its mean show up? It should show up close to this, right? So we got something that was really unusual, assuming this was the middle. So that assumption must be wrong. This must be in the wrong place. This can't be the middle if I got that. Or it's good evidence that it's not. There's always a chance I'm wrong. It could have just happened to pick a lot of people that had to wait a long time. So the last step, remember, it's a 5-step process. And this is the step that students really, well, it's easy to make mistakes here, but let me really try to focus you. Have I said anything about the claim since the very beginning? Not really. We haven't really talked about the claim. So at the very beginning, you want to know what the claim is, and then you put it in the right place. And now at the very end, I want to write a statement about my claim. Did we actually show evidence for the claim? Did we support this claim or not? So in this case, we made it far enough. So what can I do here? Was t-star greater than this?
Yeah.
Hell yes. So then we can reject the null. Support the high. Which one of those is my claim? The HO or the H1? In this case, the H1 was my claim, right? Let me say this again. Because that's my claim, right? Why did we put it there and not there? Doesn't have an equal sign. I like it. Let me go through this one more time. Once you get your answer, you look at what your claim was and you word it using that phrase. So we rejected the null, but my claim is the H1. So we support the H1. So we have found evidence to support the claim that what? And now what's beautiful is you just kind of got to go back to the problem and make sure that you tell me what's really going on with this problem in the real world. What was this problem all about? Yeah, that the mean wait time at the ZMV is greater than 15 minutes. I love it. You just tell me what the claim was. All right. So now, I'm going to shut up for a little bit and let you guys try this out.